Hello, students. Welcome to the 43rd lecture on particle physics. And today we are going to talk about Lepton-quark-symmetry. The important point here is that we know the fact that there are 6 leptons and 6 anti-leptons. Now, the leptons are divided into 3 generations: electron type, muon type, and tauon type. Then nu e minus, they form a weak isotopic spin doublet. Nu mu minus, they form a weak isotopic spin doublet. Nu tau minus forms a doublet. Then you have an antiparticle for nu e bar, e minus, e plus, and so on. And the important point is, we have discussed it times and again, that each generation obey a lepton number conservation, and we have dedicated electron lepton number conservation for the first generation, muon lepton number conservation for the second generation, and the tauon lepton number for the third generation. And independently in each process, these should be conserved. And this thing is about lepton. And for anti-lepton, we have E plus nu E bar, mu plus nu mu bar, tau plus nu tau bar. But the mass of tau minus is the same as tau plus, and the lifetime of tau minus is the same as tau plus. Similarly for E plus and E minus, mu plus and mu minus. And that is why I have not tabulated it here. But the important point is that the lepton number for these two will be -1, electron lepton number. Muon lepton number for these two will be -1, and the tauon lepton for these two will be -1. Therefore, here they are +1 for these we are calling it as particles, and these are antiparticles. Now, this is about lepton. Then we have quarks that we have discussed on the last turn. There are 6 flavors of quarks: up, down, charm, strange, and top bottom. This charge of u quark is 2/3 in units of electronic charge. This we should keep in mind, that this unit of electronic charge is silent here, but this is there. Then we have down quark, charge is -1/3 in units of electronic charge, and so on. And then the masses which are written here for 2.16, 4.67, and 1.27, these are known as the current quark masses. Therefore, these are the masses when the quarks are in the free state. And as we know that quarks never happen to be in free state, that means these are the masses which have been put by using some phenomenological model. Therefore, they are model dependent. But in general, the quark in the free state that we consider for the u quark is 2.16 MeV. But mind it, there is one catch, that when we talk about proton, which is made up of UUD quark, this mass of proton is 938 MeV. Therefore, we divide this into 3 parts roughly. Therefore, this becomes 310 MeV. While when we talk about a pi plus, which is made up of UD bar quark, and this mass is 140 MeV, then you can see that using the same argument, we cannot explain this. Therefore, the important point is, these masses which we are talking about, these are the constituent quark masses. These are the masses when the quarks are moving in a potential, and those bound states are giving rise to a proton or a pion or a rho meson or an omega meson or so on. Therefore, these quarks, when they are in bound state, they are known by the name constituent quark mass. And we will see that why is that a delta which is made up of UUD quark, this has a mass 1232 MeV, while a proton which is also made up of UUD quark, this has a mass of 938 MeV. from where that difference is coming. We will see that we will talk about spin-spin interaction, and it is similar to what you have in a spectroscopy, hyperfine structure. Similarly, here also we will talk about that. But what we know is that there are quarks, there are leptons, and today we are going to talk about lepton-quark symmetry. Notice that leptons are also point particles, quarks are also point particles. Leptons participate in electromagnetic interaction, the charged leptons, as well as in weak interaction. While neutral leptons, like neutrinos, they participate only in weak interaction processes. In the case of quarks, all quarks are assigned baryon quantum number. This is 1 by 3rd. So that when you have 3 quarks, 1 by 3, 1 by 3, 1 by 3 will add up to give you the baryon number of the proton or baryon number of the delta and so on. But the important point is that when we are talking about quarks, all have been assigned the same baryon number. It is not like in the case of leptons where we have dedicated electron lepton number for electron and its neutrinos and antiparticles, muon lepton number for muons, neutrinos and antiparticle and so on. They have common baryon number. Similarly, for anti-U, anti-D, anti-S, anti-C, etc., the baryon number is minus 1 by 3 and charge will be reversed. But what is more important, that charged leptons only participate in electromagnetic and weak interaction processes. Neutral leptons only participate in weak interaction processes, while quarks participate in strong interaction, electromagnetic interaction, and weak interaction processes. They are point particles like leptons, but here the important point is that they are constituents of nucleon or lambda or sigma, and those are the particles which participate in strong interaction. Therefore, quarks participate in all the 3 interactions. Now, with this concept in mind, let us talk about first the interaction of leptons. Suppose I am talking about the interaction of a neutrino with an electron. Now, when we are talking about an interaction of neutrino with an electron, what will happen? How this can take place? The answer to that is neutrinos only participate in weak interaction process, and in weak interaction the mediating quanta can be W plus, W minus or Z0 bosons. As I have told you that without a mediating quanta you cannot think of an interaction, and therefore what is happening is that a neutrino is emitting a W plus boson, and that is getting converted into an electron. A neutrino which is emitting a W plus boson and is getting converted into an electron. And at this vortex, what we will realize that the total lepton number arriving at this junction must be equal to the total lepton number leaving from this junction. Otherwise, that process will not be an acceptable process. Number 2, total charge arriving at that junction must be equal to the total charge leaving from this junction. Therefore, whenever I am drawing a diagram which is known by the name Feynman diagram, that a neutrino is emitting a W plus and changing its flavor to electron, the two concepts that we have to keep in mind, that lepton number arriving lepton number in must be equal to lepton number out. And mind it, it should be of same generation. And therefore, that means particularly I should write it as electron lepton number in must be equal to electron lepton number out, or tau lepton number in must be equal to tau lepton number out. Or the other point which I am telling you, the total charge arriving at the junction must be equal to total charge leaving from that junction. That means you see zero charge is arriving because neutrino is a neutral particle. How many charges are flowing out? -1 for the electron and +1 for the W plus meson. Sum them up, that will be 0. 0 is arriving and 0 is leaving. Neutrino is arriving and electron is leaving. And that means when we are talking about lepton number conservation, you may say that by writing like this, a Z0 gets emitted from a nu E, and this nu E gets converted into E plus. We are conserving charge because that, and in Feynman notation, incoming outgoing antiparticle is represented by an inverted arrow. Therefore, we have to keep this in mind that incoming particle to the vortex is represented by an inward arrow, while this is for particle, this is incoming particle, an inward arrow, while an outgoing particle from here, or let me first write for antiparticle, incoming antiparticle, this will be represented by an outward arrow. Therefore, this is representing a particle which is coming to the vortex, like electron, like proton, like quark, like muon, like neutrino, whatever you talk about, all the particles arriving at the junction will be represented by an incoming arrow, while a positron, an anti-neutrino, a mu plus, a tau plus, an anti-proton, etc., will be represented by an outward arrow going towards the vortex. Similarly, if an electron is coming out like this, therefore a particle going out is represented by an outward arrow from the vortex. This will be true for muon, neutrino, proton, neutron, whatever particle you talk about. But an outgoing antiparticle will be represented by an inward arrow from the vortex. And this will represent as that an outgoing particle or an antiparticle is going out. And therefore, here a particle is going out, here an antiparticle is going out. Here a particle is coming in, and here an antiparticle is coming in. Therefore, when I am talking about a neutrino is coming, a positron and a Z0 in the outgoing state, a neutrino emits a Z0 and gets converted into E plus. Charge conservation is there, but as you can notice, total lepton number arriving at this junction is +1, while the total lepton number leaving from this junction is -1, and therefore this is not an allowed process. Therefore, at this vortex, only an electron can go out. You can have a Z0 exchange, but that Z0 exchange can be with a that Z0 exchange can be with a nu E or with an electron, an incoming electron and an outgoing electron. Therefore, you can think of a neutrino is coming, it is emitting a Z0 and it's going out. You are conserving charge, you are conserving electron lepton number, arriving at the junction is +1, electron lepton number leaving from that junction is +1. You are conserving electron lepton number, you are conserving charge, therefore this should be an allowed vortex. While if you talk about an electron emitting a Z0, it will remain an electron. It cannot change to a muon. It cannot change to a tauon, because then lepton number will be violated, though you are conserving charge. Therefore, this is important point, that at each vortex we have to conserve lepton number, we have to conserve charge, and the rule tells us that the incoming particle will be represented by an inward arrow, while incoming antiparticle will be represented by an outward arrow. Outgoing particle will be represented by an outward arrow, and outgoing antiparticle will be represented by an inward arrow. This is Feynman convention. Therefore, the important point is that when we draw such a picture, we have to keep in mind that where the particle is moving, and then what is its charge, and what is, if it is a lepton, what is its lepton number, if it is a baryon, what is its baryon number. Okay, now the other question that you may ask is that when we are talking about electrons participate in electromagnetic interaction also, and the quanta of electromagnetic interaction is photon. Therefore, you can also represent it by an electron emits a photon and moves in some direction, while the other point that I told you, the electron emits a Z0 and it's move out. Now the important point is, this is an electromagnetic interaction process and this is a weak interaction process. We know that weak interaction cross section is almost 8 order or 10 orders of magnitude is smaller than electromagnetic interaction process. This means that particles are the same. From where this difference is coming? The answer to that is, the difference is coming from this coupling of electron with a photon or electron with a Z0. This is one difference, that why the cross section in the case of weak interaction is 10 power minus 40, while in the case of electromagnetic interaction it is 10 power minus 32 centimeter square, when we are talking about electron scattering. Now this electron scattering means electron in the initial state as well as electron in the final state. This is taking place via photon exchange as well as Z0 exchange. But nobody talks about Z0 exchange. This is because of two reasons. One is the coupling of electron with a Z0 is much weaker in strength than the coupling of electron with a photon. Now, this is one difference. And the other difference is the propagator. Photon is a massless particle, while W has got a very heavy mass. When this is there, Z0 or W, then for each matrix element, you will get a factor of 1 by mw square or 1 by mz square. While here, if this is carrying a 4 momenta q, this will be just proportional to 1 by q square. And this mw square in general, for the energies that we talk about, 500 MeV, 1 GeV, 5 GeV of particles. These energies that we talk about, this mw square is much larger than, see, mass of w meson, if you recall the properties of mediating quanta, it is about 80 GeV, while mass of z0 is 90, about 90 GeV, mass of z. Therefore this is 1 by 80 square. This 1 by 80 square is at the matrix element level, but we know that from Fermi's golden rule that we have matrix element square, and therefore this will be 1 by mw to the power 4 or 1 by mz to the power 4. And when it is 1 by mw to the power 4 or mz to the power 4, this mw or mz to the power 4 is like an elephant in front of q to the power 4, and that will suppress this process a lot. Therefore, one is the coupling strength. Here we write that coupling strength as GW for the weak interaction, or GZ for the, if there is a Z exchange, and this we write it by the general convention alpha, where alpha is known as the fine structure constant. This we will discuss in the class. But the important point that you have to understand is that electromagnetic interaction cross section is much larger in strength than weak interaction cross section. Though in both the cases we are talking about the same particles. We are talking about electron scattering. We are talking about a muon scattering, and so on. Why is that the difference is arising? This is arising because of the exchange mass of the exchange particle, because at the level of matrix element, it is the 1 upon mass of the exchange particle square in the case of W and Z bosons, while in the case of photon, it is just 1 by Q square. There is a factor of Q square here also, but that factor of Q square we don't take into account, because that Q square for 1 GeV particle or 500 particle or 2 GeV particle is much smaller than the mass of the W boson or mass of the Z0 boson. Therefore, one factor is this mw to the power 4 is much larger than q to the power 4, and since this comes in the denominator, therefore you can see that this value will be much smaller than the contribution that you are getting from 1 upon q to the power 4. And the other difference that we are talking about, that the coupling strength, the electron is coupled to the photon, this coupling is much larger in strength than the coupling of electron with a W boson or electron with a Z boson. And this we will discuss in the next class, that what is the coupling strength and how we can estimate broadly the cross section. But the important point is, when we talk about Lepton-quark symmetry, we have to keep this in mind, that we have an electron, we have a muon, and this electron is giving rise to a neutrino. This can only happen when the emitted particle is a W minus. Electron emits a W minus, gets converted into nu E. Muon emits a W minus, gets converted into nu mu. Or you can say that a nu E emits a W plus, gets converted into electron. A nu mu gets converted into muon by emitting a W plus. Similarly, an incoming positron emits a W plus and gets converted into nu E bar. An incoming mu plus emits a W plus and gets converted into a nu mu bar. See here, this is outgoing muon type antineutrino. Why we are putting an inward arrow? Because the Feynman rules tells us that for outgoing anti-particle you have to put an inward arrow. Therefore, this is the inward arrow for the incoming anti-particle. This is inward arrow for the outgoing anti-particle. Now, similarly, you can say that an anti-neutrino is coming and it is emitting a W minus and getting converted into E plus, or a muon type antineutrino is coming, it is emitting a W minus and getting converted into a mu plus. Now you see, this propagator at all these places are the same. All of them are leptons. All of them are point particles. Then the lepton symmetry tells you that the coupling strength of here would be the coupling same as the coupling strength here. That would be the same as the coupling strength here. That would be the same as the coupling strength for all these places. That let us represent it by GW, the coupling strength, the strength with which a W boson couples with this particle, or a W boson couples with a neutrino or couples with mu minus. They are of the same strength. And that means whether I am talking about the first generation lepton as well as anti-lepton, second generation of leptons as well as anti-leptons, what I am telling you that when it is participating in interaction, whether that interaction is via W boson, or similarly I have demonstrated it in the previous slide for the neutral exchange boson, that is a Z0 boson, the strength of the interaction would be the same, and that means nu E emitting a Z0 or nu mu emitting a Z0, the strength of the interaction here would be the same. It will not change. That means if you are talking about two generation of leptons, then what I am telling you that the strength of the interaction, the nature of the interaction, they are not going to change. If neutrino will interact with electron only via a W plus exchange or a W minus exchange. A nu mu will interact with mu minus only via a W plus exchange, or because see here there is an exchange of charge. Nu mu is getting converted into mu minus. Nu mu bar is getting converted into mu plus. And that means this is only possible when there is an exchange of W minus or W plus. And that means when there is an exchange of W bosons, then you are talking about a neutrino getting converted into corresponding charged lepton, or an anti-neutrino is getting converted into a corresponding charged anti-lepton, and so on. For the two generations, what I am telling you that the strength, whether you are talking about W exchange or you are talking about Z exchange, the strength of the interaction, the strength with which a neutrino couples with a W plus boson, or anti-neutrino couples with a W boson, or a nu mu bar couples with the W boson, that strength has been found out to be the same. What is the difference? The difference will be whether you have an electron or we have muon or you have a mu plus, the masses will be different. That means the kinematical effect will be there, but the strength of the interaction and the propagator will be the same. Now in the next class, we will talk about the quarks, and here we have stick to two generations only, because first we will talk about the two generation of quarks starting with U and D, and then when we will introduce C, at that time we will say that there a tau lepton was observed, and corresponding to that there should be a new tau, and then first, second to third generation of leptons we will discuss, and similarly we will extend it to quarks. Let us stop here. Thank you very much.